طيب بسم الله الرحمن الرحيم. Today we're going to start the last chapter. So satellite systems, they gained momentum a while back, and then they damped down a little bit. So it has been revived again, especially with the deployment of new satellites and some factors that led to wide deployment of satellite systems, and many countries, many governments, many even commercial companies, they are starting to really come back to deploying satellite systems for reasons that we will need to discuss today. طبعا one of the biggest deployments is Starlink, so we want to understand also what has led to reviving the use cases for satellite systems again after it has damped down a little bit, or maybe the applications changed. So we need to talk about some historical chronological events that happened where satellite systems have actually evolved, and what are the use cases, the applications, what are the basics related to satellite systems, and what are the different types of satellites, also how localization, how handover is performed, why do we need to do routing for the case of satellite systems, and so on. So these are the main topics that we need to cover in this chapter. So historically, these are some of the events that happened that where countries started to have interest to deploy satellite systems for different reasons. It started, of course, with the with this publication of extraterrestrial relays, and of course governments since then, they started to have a race of trying to tap into these technologies to maintain control or maintain superiority and so on and so forth, because satellite systems have like some strategic applications, like espionage, for example, like spying and getting some information that nobody else has or can tap into, and so on. Of course, in a later stage, they have become a commodity, and they have started to to have more applications and diverse applications, even commercial applications. For example, مثلا اللي هو ال GPS اللي هو Global Positioning System. It started as a military project. It was based on satellites, and the fact that you do triangulation for between 3 satellites to know where your location are in any point on Earth and stuff like that. So that at that point it was like a big technology, but and it was only related exclusively to military applications. But later on, GPS have become very common, and everybody is actually using it as as a service today. The first deployment for satellite systems, it was named Sputnik, which was deployed by the Soviet Union at that point. So there was a big race, of course, between USA and Soviet Union. So they deployed the first Sputnik, and that was, of course, very primitive. It did not provide any data services at all, and it was only to just use it for some espionage and spying and things like that. The US, 3 years after, they deployed ECHO, which is a satellite that's used only to reflect signals. Just to reflect signal. It takes from physical layer. There was no intelligence whatsoever in this. So it takes signal and it actually, reflects it again on Earth. So you just use it to increase coverage or something like this. So the raise has continued, and also the US have deployed what we call SYNCOM, or satellite SYNCOM, and that was the first geostationary. So we need to know what geostationary means here. So geostationary here is a specific category of satellites that we need to understand what it is. We'll talk about it in a minute. And then we started to have like some commercial applications. So that started with Intelsat. And Intelsat is one of the common, and it exists until today, or another name is called Early Bird. And that was only for TV. So it broadcasts TV channels. And then later on, they have another commercial satellites, which is like Mirasat, and then Intmarsat, and so on. So these are different deployments of satellite systems that started to offer either marine communication, and by marine communication we mean that we'll see in a minute that we have like a gateway on Earth, which is like a ground-based station, which receives a signal or data from the satellite, and then this gateway will feed or will relay this information to different types of networks, whether it's GSM network or under marine communication or something like this. So, Mirasat, for example, is used for marine type communication, where you have a gateway which is set up on ships, or it's like some ground-based station close to the sea, and then it feeds that information to like submarine communication or something like this. So that's a special type of network. So the gateway is sort of the bridge between the satellite communication and any type of other network, whether it's GSM, ISDN, PSTN, submarine communication, anything like that. So we'll talk about the architecture in a minute. So طيب, so بعدين طبعا يعني in 2000 بقى we started to have the launch of SpaceX, and SpaceX was like يعني a big commercial company that started to even have some partnership with NASA to try to deploy different constellations of satellites in low orbits. We'll talk about this. And in 2018 or 2019, they started their mega project of Starlink, which deployed over 6,000 satellites in low orbit that can provide a huge amount of data rates. And that started to really revive the use cases for satellite systems drastically, even nowadays. So, and of course, the biggest potential for satellites is that they can cover some spots on Earth that no other technology can cover. So some rural areas can only have coverage through satellite systems. So despite all the infrastructure that we have, there are some remote areas on Earth that they do not have coverage even until today. With satellites, these rural areas and remote areas, they can have wireless coverage easily through satellites. But the problem becomes that with satellites, of course, there is a huge amount of delay and latency, and there are some issues that we have to talk about. And that was that's why Starlink was revolutionary, really, in terms of trying to use satellite communication to provide very high data rates. So that was exceptional. So it's reaching to hundreds of megabits or close to gigabits per second. So in terms of applications, traditionally satellites were used mainly for getting some satellite images, and based on that they use it for weather forecast or weather analysis, or they use it for TV channels. The good thing about TV channels is that it's broadcast channels, so you just take the TV signal and just broadcast it. So there is no like two-way communication. So it's one way. So with that, it's satellite still can provide good broadcast services because does not require two ways. So the delay is actually downlink, there's no delay uplink. So there is no two-way communication. So TV broadcast was traditionally possible using satellite communication, and of course for military, it all started, with military applications and with applications such as espionage and so on, and of course GPS, which was the global positioning system. So any device on Earth can use 3 satellites or the signal from 3 satellites to evaluate or to estimate with some accuracy the actual location in terms of latitude and longitude of that device. It wasn't until possibly sometime in 1990s that we started to have some telecommunication services using satellites. Of course, the biggest obstacle was the high latency, because the propagation delay, as you can imagine, any mobile station, in order to send a wireless signal to the satellite and then comes back. Of course, the latency we're talking about, in some cases, the latency can be close to a second, which of course limits the throughput or the bits per second. So the bits per second, the throughput actually in satellite systems for telecommunication satellites, it started only with 10 bits per second, or with, that was a big, upgrade that they have reached 10 kilobits per second with some satellites only in low orbits. We'll talk about this. But nowadays we started to have really very high data rates that really have made satellite communication attractive again. So basically, satellites can work as backbone for global networks. So some GSM networks can use satellites to extend the coverage, right? So they can use satellites as relays to extend the coverage and provide more resources in the network. It's not a replacement for GSM, but they can be used as backbone and relays, which can provide coverage to remote areas and rural areas which otherwise do not have actual base stations, ground base stations, deployed. So in that case, satellites are used as a complementary infrastructure to GSM or AMS or third generation wireless. So that's how it looks like in terms of satellite architecture. So so each satellite on Earth have what we call a footprint. A footprint is like the coverage of this satellite. This footprint can be subdivided into what we call spot beams. And what spot beam means is that the satellite itself has multiple antennas. So each antenna can in fact create a specific spot beam. And this spot beam provides also what we call intra-satellite handover, similar to Bardo intra-PTS handover. So the mobile users can move, and based on that, they can hand over from one spot beam to another, which means that on the satellite, they move from one antenna to another. Okay? So that's the footprint for one satellite. So this is the mobile user, and this mobile user in that case, in the past, we used to require the user to have special hardware because this requires, of course, transmission powers in rate that's not usual. By the way, this mobile user link can use transmission power in the range of 1 watt or maybe 2 watts or something, which is, of course, it's very high, and that's why the mobile users devices they used to be bulky, relatively speaking, and use high transmission power and large antennas and stuff like that to be able to communicate with the satellite. Nowadays, we're using 24 gigahertz and 40 gigahertz, and in low orbits we can use low transmission power, as we will discuss, and that facilitated the fact that mobile devices are becoming smaller and so on. So we have the mobile user link, okay, and then the satellite are used, as we said, as a backbone to the networks, whether it's a GSM network, PSTN, ISDN, or submarine communication, or whatever. And the satellites can relay the traffic either to a ground gateway. So this ground gateway acts as a bridge. This ground gateway maintains some association between the mobile user and the different satellite. A base station or a gateway can, in fact, communicate with multiple satellites, right? In which case, it has information about which user is connected to which satellite at any point of time, okay? And at the same time, it interfaces the satellite communication to the different types of technologies, whether it's GSM, 3G, 4G, whatever, okay? There is also a possibility for some satellite systems that provides inter-satellite link. So you have also the ability to do like mesh communication or satellite-to-satellite communication. And usually that uses, of course, microwave link or microwave communication, or laser communication. Okay, like for example, SpaceX, they use laser communication. So communication in very high frequency, and it uses, of course, in that case, we use a line of sight, and we use directive antenna to try to maximize the throughput between the satellites. And that also happens only in satellites that are deployed with high constellation. As we will see, for some satellites, if they have very large footprints, usually with only 3 satellites, you can cover the entire Earth, okay, given the large footprint. So in that case, you don't need any ISL. You don't need inter-satellite link because, of course, the coverage is fairly large. So you only need to relay to the ground gateway, and the gateway will take care of the communication. We don't need any inter-satellite link. But in other satellite systems, they are deployed with high constellation, in which case you have potentially sometimes tens of these satellites deployed in a certain orbit, or sometimes hundreds. And as we said, for example, Starlink have more than 6,000 satellites, in which case the density of these satellites are huge. And in that case, you definitely need some kind of inter-satellite link, because these inter-satellite links can be very fast in that case and avoids, communication to Earth back and forth, right? Because, of course, here we have a routing issue, right? So when the satellite receives the wireless signal, it can send it this way or this way. So you definitely have some routing function, right? So of course, if the satellite decides to send it to the gateway, then the latency associated to this is high, especially if the gateway has to send it to another satellite. So instead of going this way, right, I can go this way, and this way. So this would be relatively faster. So depending on the constellation of these satellites, we can try to avoid communicating to the ground gateways. So that's a routing issue. Okay. Any question here? So this is mainly the اتفضل.
So the satellite work as a relay, or itself has the connection, internet connection?
As a relay, it works as the backbone to the network. So it receives the information, and then it has to send it to a gateway to feed it to the GSM. So you can think of this gateway as the mobile switch center for the satellites, So this gateway really acts as the mobile switch center, MSC. So it acts like the brain that communicates with the different satellites. It has the association between the user and the different satellites, so it knows exactly how it controls actually the routing as well. And it receives signal from multiple satellites. So it acts as like the brain, and it facilitates the interface to the different networks, right? both yes. Analog we're talking about يعني physical layer اللي هو الايكو satellite مثلا. It works like physical layer. It acts like it reflects the signal as is. It doesn't do anything. It reflects the signal, only extends the coverage. That's it. But of course, other satellites, and especially the satellites that we have nowadays, they are digital, of course, digital. They deal with digital signals. So they have to convert the signal from analog to digital, and they do lots of processing and smart routing, localization, things like that, and then they send the information to either to other satellites or to the ground-based stations and so on. So it's digital يعني. ماشي؟ يعني طبعا the functionality for these satellites evolved over the years drastically. So we'll understand about some basics for these satellites. There is interesting phenomena that, of course, satellites usually in different orbits, assuming that they circulate around specific يعني virtual orbits يعني, they have some forces that sort of control the movement of that satellite. Of course, they have the attractive forces, which is based on the mass of the satellite, and this is the attractive forces, which is proportional to the mass of the satellite, and the acceleration, of course, the gravitational acceleration, and this is the radius of Earth, and this is the distance of the orbit from the center of Earth. Okay, so this is the radius of Earth, and this is the distance of the orbit that the satellite circulates over. So this is the gravitational force, and of course there is the centrifugal force. Centrifugal is that any يعني physical object that sort of circulates like this, it has a force in that direction, right? The centrifugal force. So this centrifugal force is based on the mass and the distance and the rotational frequency. So the faster you rotate, the higher the power in that direction. Okay, so these are the two forces that sort of control the movement. So in order for a satellite to circulate in a specific orbit, it needs to have like some balance between these forces. They don't have to be equal. They don't have to be exactly equal. But if they are equal, then there is a specific phenomena that we need to talk about. And by controlling the speed of the rotation and so on, you can balance, because in that case, if the centrifugal forces is more or less, it makes the satellite move outside the orbit. In that case, the satellite needs some fuel and things like that in order to correct its location to go back to the orbit and circulate around the orbit, right? So if you have a specific balance between the centrifugal forces and the attractive forces, you use the minimum amount of fuel and things like that to control the position of the satellite. واضحة دي؟
دكتور, if they are equal, the FG and if the central force, it will be geostationary, correct? However,
not necessarily. Only if you have a specific rotational speed. If you have a specific rotational speed.
It's not the angular velocity.
لا إيه؟
It's not the angular velocity.
ما هو الانجولار velocity اللي هو الروتيشنال سبيد. ما هو الانجولار velocity اللي هو إيه؟ اللي هو rotational speed.
Yes.
يعني الانجولار velocity دي هي 2 pi f, and f is the frequency of rotation. صح؟ So if the two powers are equal, the satellite can keep itself in a specific orbit and circulate in an equal distance from Earth, right? تمام. But that's not geostationary. Geostationary has two conditions. The two forces are the same and the rotation speed equal to the rotation of Earth. معناها ان the satellite covers the same footprint on Earth, right? And it circulates ماشي with that spot. So the footprint on Earth does not change. That's why we call it geostationary. Okay? Because Earth is circulating. ولا في حد believes otherwise, because some people are believing otherwise nowadays. Earth is circulating. ماشي عشان يعني Earth is circulating. خلاص. That's a fact. ماشي. So if the satellite circulates with the same speed, this means that it covers one fixed footprint on Earth. In that case, it's geostationary. ماشي. But if the forces are equal, that doesn't necessarily mean geostationary. Okay, that only means that the satellite can keep itself in the same orbit. But the speed can change, which means the footprint on Earth may change. واضح كده؟ تمام؟ So since طبعا ال G is fixed and R is fixed, which is the radius of Earth, unless you believe otherwise again, the mass of the satellite, of course, is in the range of طبعا when we say the two forces are equal, the mass goes away, right? So it doesn't depend on the mass of the satellite, because if you make the two forces equal, M it's agnostic to the mass, right? It's based on the radius of Earth, of course, and the rotational frequency. This F is the rotation. How many times it rotates, or how many circles it rotates on Earth. واضح كده؟ So when we make the two forces equal, and you would like this to happen as much as possible, because then it allows the satellite to use the minimum amount of fuel to keep correcting its position, right? So it's controlled by physics that it keeps itself in the same orbit with the minimum overhead. Okay? If this balance breaks, then you always need a extra force, extra torque to go back to the correct position. And that requires some fuel and things like that. واضح كده تمام? So this is the relationship now that controls the balance. كويس? So this is the distance of the orbit, or this is the radius of the orbit from the center of Earth. واضح كده؟ So what is the relationship of this بقى to the rotational frequency, or to the period of rotation around Earth? So this is what this relationship explains here. So as this number, this is the how many. So this means that every 24 hours you complete one rotation to Earth, right? Of course. So this number is familiar, صح? So we're supposed to have the Earth is supposed to circulate every 24 hours. If this synchronizes, then we have, this point is supposed to be here, by the way. We have this point, which is an interesting point, that if the rotational frequency is every 24 hours, in that particular case, we have a geostationary satellite, which means that the satellite, not only it rotates with balance between the centrifugal forces and the attractive forces, but it also covers the same point on Earth. And that's why all the geostationary satellites, they actually circulate around the equator as well, because again, the Earth is supposed to rotate around from the equator, صح? If you put like the North Pole and the South Pole, the Earth rotates this way. So in order to be geostationary as well, you need to circulate in that orbit, هو aligned with equator. ماشي? That's when you have a geostationary satellite, and the footprint does not change over time. Okay. But that only happens in that very, very far distance. So it's about 36 kilometers, 36,000 kilometers, sorry. 36,000 kilometers. And as you can imagine, this is a very high elevation, altitude. Very, very high altitude, of course. And that's why geostationary satellites, they have extremely large footprint. So typically, this footprint is around 35% of Earth, which means that technically you can have only 3 geostationary satellites to cover the entire Earth. Okay?
Do they have standards for?
No?
Do they have standards for?
They do, yes. They do have standards for satellite. Yes, they do have standards for
Just
satellites.
like frequencies.
Yes, yes, yes. Same thing. Yes. طيب, of course, we have some parameters that characterize the circulation of satellites in certain orbits. We have what we call inclination. Inclination here talks about the fact that if you have the imaginary plane of the equator, if you have like the equator and there is like imaginary plane that sort of cuts Earth at the equator كده اللي هو this plane, ماشي? Any arbitrary orbit, which could be circular or elliptical, by the way. So this is in general an elliptical satellite that moves not in a circle, but in elliptical orbit. ماشي? In elliptical orbit here means that technically you need to have extra amount of fuel to keep correcting because it's not going to be balanced. In certain points, you have different forces, صح? So you're not going to have this, but you cannot maintain this balance unless you have a circular orbit. And that's why circular orbit satellites are much, much more common. The elliptical ones are much less common. Even Starlink nowadays, they use circular orbits and in the LEO, low Earth orbit category. We'll talk about this. But in general, if this orbit is elliptical like this, right? If it's in a specific plane, the inclination talks about the angle between the equator plane and this inclination. Okay? So that, of course, affects the fact that the coverage of the satellite to a specific point on Earth changes over time. If you have a geostationary satellite, this means that, first of all, this elliptical becomes a circular, and not only that, the inclination becomes 0, okay, and the rotational frequency becomes every 24 hours. Only in that case, you cover the same point on Earth, and you keep covering this point all the time, right? But if you have elliptical orbit like this, you have what we call البيرجي. Perigee is a specific point which it's actually represented on that elliptical orbit such that the distance between this point and Earth is the shortest. واضح كده? So this perigee is a point. Of course, you have 2 points that fulfill that definition. You have a point here and a point here, where this point is the closest to the Earth surface. So this point is called the perigee. ماشي كده؟ Of course, one thing that characterizes this point, as you can imagine, is that you can use the lowest transmission power in that case. But you definitely have to spend huge amount of fuel and stuff like that to sort of balance the attractive force with the centrifugal force. واضح? So there are some special things that characterize this point. واضح? So when do I have the lowest transmission power in any orbit is at this point. ماشي كده؟ So this is the inclination. Another more important actually parameter that characterizes the footprint of the satellite is what we call the elevation. Elevation is the angle of imaginary beam like this and the footprint on Earth. Of course, this elevation angle, you can imagine that if you have this elevation angle like 90 degrees, this means that there is like this line here will be the shortest, in which case you have good coverage on the Earth's surface. And if this elevation goes really very, very small, this means that the coverage of the, يعني طبعا this is directed through the antenna, right? If you direct the antenna this way, so the elevation keeps getting smaller. If it's smaller than usually 20 degrees or 10 degrees, usually you have no communication whatsoever. So if the elevation is really small, especially with the natural phenomena like rains and things like that, you start to have no communication whatsoever. So you would need to have the elevation close as much as possible to 90 degrees in order to have good communication, right? So if this elevation is like 20 degrees, or imagine this is like 20 degrees or something, then the communication becomes really, really faded, deeply faded, and in that case you will not have. طبعا, of course, if you assume the elevation is really small, you can have wider footprint, but in different parts of this footprint you will have no communication whatsoever. Okay, so the smaller this elevation is, the more noise effect you're gonna have, and in that case you have no efficient communication whatsoever. طيب. So in general, you have elliptical or circular orbits, and we talked about what are the pros and cons for each one. Circular orbits, usually you can sort of balance the attractive forces and the centrifugal forces easily, in which case يعني you need minimum amount of يعني correction to the position of the satellite. Elliptical orbits usually are much trickier to maintain the stability of the satellite. Complete rotation time, of course, depending on the distance. ماشي. So if you are close, you need to rotate يعني slower, and you can cover a full circle around Earth with lower speed. But if you are very far away, especially in the geostationary orbit, then you can circulate around once every 24 hours, and in that case you have the geostationary phenomenon. Inclination angle between the orbits and the equator, and the elevation angle between the satellite and the horizon, lower imaginary line across the Earth. And in many cases, we need the line of sight communication for the satellite to have efficient communication, although that's not always achievable. So there are some, of course, obstacles through building. So we still have multipath fading and so on, and that affects the communication of the satellites. If we're talking about the uplink, is the connection between the mobile user and the satellite, and the downlink is the connection between the satellite and the usually the base station or the gateway. ماشي. And usually this uplink and downlink are separated using FDD, or they use different frequency for uplink and downlink. Okay. TDD is extremely inefficient here due to the high propagation delays. So we can have full duplex, which means that we send uplink and downlink at the same time, but on different frequency, rather than having to do it sequentially. If you do it sequentially, propagation delay increases the total delay drastically. So you don't want to do this. So that's why we use typically FDD for the case of satellites. Type. Of course, in terms of loss, the loss here is mainly due to, of course, propagation loss, and that propagation loss is evaluated through this equation. Frequency here is the carrier frequency, not the not the circulation frequency. Keep that in mind. So this is the carrier frequency in that case. Satellite communications, they usually use gigahertz frequency, and Starlink, I believe they use around 24 to 40 gigahertz frequency, carrier frequency. طيب. Of course, parameters like sending power and gain of the sending antenna. Of course, the gains of the antennas are they have large form factor, and usually they have very high gains. Distance between the sender and the receiver, of course. These are all factors that affect the loss. And of course, there are varying strength of the received signal due to multipath fading, especially for the satellite communication, because what's really different between satellites now and the ground-based stations is that here we are talking about moving relay nodes. So not only the user is mobile, but also the relay nodes are mobile, right? So that really creates a varying multipath fading pattern, right? Because the user is mobile, the satellite is also circulating around Earth. And this circulation makes things much more complex, because now if the satellite is geostationary, this means that it covers the same footprint. So you don't have to really do lots of handover between one satellite and the other. But if the user is moving and the satellite is also moving and moving fairly fast, we're talking about low orbits where the satellites can move fairly fast, right? So in that case, the user has to actually hand over between satellites very frequently. And that creates some varying lower multipath fading. And also, due to that, you have also some interruptions, because if we don't have line of sight between the mobile user and the satellite, or between the satellite and the ground-based station, usually between the satellite and the ground-based station is okay, but usually the trickiest part is between the moving mobile user and the satellite, because both of them are moving. So that sometimes creates some shadowing. Shadowing talks about the fact that you have obstacles, and that breaks the line of sight, and that affects deeply the communication. تمام كده؟ Like shadowing that you can try it very easily. I usually have this shadowing many times when يعني مثلا لما تكون مشغل السماعات مثلا اللي هو الايبودز اللي هي الايبودز okay, just try to do this. خلاص you cannot have communication when you do this. خلاص breaks everything. This is what we call shadowing. خلاص يعني it's not multipath, it's complete blocking يعني complete shadowing. خلاص you block the communication. تفضل تقول حاجة؟
دكتور, the loss here is the delay ولا data loss?
لا loss, the amount of loss. This affects the delay, of course, and affects the throughput. This is the amount of loss. What we are trying to say here is that this loss is proportional to the square of the carrier frequency. So as the carrier frequency goes high, this loss becomes more. And how do you compensate for this loss? You compensate through some link margin. Like مثلا link margin ده معناه ايه? It's like in order to have communication, you need to have transmission power around مثلا 1 watt. لا, I'm gonna have it 1.2 watt. Okay? Because this loss varies depending on distance, depending on multipath fading, and so on. So we have to have like some link margin. So I'm going to have 1.2 watt as a transmission power just to compensate for any noise or multipath propagation or something like this. ماشي? But this is the loss, amount of loss. ماشي? Of course, satellite diversity here talks about the fact that we can have different signals between the mobile user and the different satellite, and that may cause the user to hand over between one or more satellites, and or spot beams. So you can move from one spot beam to another, which means that you hand over from one antenna to another. So you can try to use that level of diversity to maintain different communication. Of course, if you switch from one antenna to another, that affects multipath propagation. It affects the amount of loss due to noise and so on. So you see which one gives you the highest signal strength, and then you can hand over from one antenna to another or from one satellite to another and so on. So that's the amount of loss. This measures the amount of, or the attenuation loss, okay, as a function of the elevation, the angle elevation. And as you can see, the loss is really high when the elevation is 10 degrees or less. As we said, 10 degrees or less makes the angle between the line or the beam from the satellite to Earth and the horizon, okay? This angle is very small. So if it's 10 degrees or less, this means that the loss is really high. You cannot have communication in this area at all. And this loss is affected by whether we're talking about rain or fog or atmospheric absorption and so on and so forth. Okay? So what we're trying to say here is that if the elevation is low, then you cannot have communication. You cannot have efficient communication. ماشي كده؟ طيب. So there are 4 types of orbits بقى. There are 4 types of orbits. We have the geostationary orbit, which is, as we said, around 36,000 kilometers. And that's when we have a satellite having very large footprint, and this footprint does not change if it circulates with the same frequency like the Earth circulation. And in that case, we have the geostationary satellites. So geostationary satellites, usually, they have pros and cons, which we need to talk about. We have the MEO, or the medium Earth orbits, and these are usually between 6,000 and 20,000 kilometers. This is an example, or what we call intermediate circular orbit. This is a specific satellite system that has been deployed in these orbits. And there is the LEO, and we'll talk about why do we have only 3 categories and not more. LEO is the most common, really, now, especially nowadays, and we'll talk about why. And this is between the 500 and the 1,500 kilometers. Okay? And of course, there is the highly elliptical orbit, which is, this is very, very uncommon. Because as we said, this is very challenging to maintain the balance, and you need a huge amount of fuel in that case to keep correcting the position of the satellite, because it's very hard to maintain the balance between the centrifugal forces and the attractive forces. So you have to keep correcting the position of the satellite. So usually, the lifetime of these satellites in elliptical orbits is usually very, very small, in the range of months, not even years. In geostationary, by the way, you could have a satellite for مثلا 10-15 years. No significant maintenance, because there is balance. It rotates, and even the number is low. You can have only 3 geostationary satellites to cover the whole Earth. But of course, that doesn't mean that they have no disadvantages. We'll talk about the disadvantages in that case. But nowadays, this is the most common one. Of course, these 3 are all circular, of course. You know that. صح? So the first 3 are all circular orbits. Only the last one is elliptical. Type. So these are the 3 types of orbits now laid over the atmospheric graph. So if you remember from geography, in primary school or something, we have the Earth, of course, and this is there is what we call the vanillin belts. اسمها أحزمة فانالين. كنا أخذناها في
اللافا قصدك.
هي هنا في some particles that really blocks any type of communication. You cannot have يعني this that's why these elliptical orbits are very very tricky, because they actually have to cut through the Van Allen belts, and in that case, in this part, for example, you cannot have communication. Okay, it makes it very very hard to have any kind of communication in these ranges, and that's why we have only 3 categories, because this is the Leo, which is يعني below the first Van Allen belt, and there is the Mayo, which is between the 2-1, and there is the Geo, which is outside. Okay. ماشي كده? So you have the Van Allen belts. They have ionized particles that sort of makes the rotation of the satellite really tricky in that case. تمام كده؟ So these are, for example, GEO, the Inmarsat, which is what we talked about, which is used for maritime communication. This is one example of a GEO satellite. ICO or Mayo is one of the examples, and of course in LEO we have many examples. We'll talk about many of these, like Global Star, RDM, and of course Starlink. Now they use LEO as well, and I think Hellsat نفس الشيء also uses LEO. I'm not sure if you know, but in Qatar University here we have a project for CubeSat. Have you heard about this? CubeSat. Yeah, so CubeSats are very, very small micro satellites, very small. It gets also deployed in a specific orbit, but the launching, it has to be done through very low number of companies around the world. Maybe 3-4 companies, they do the actual launching. But what many organizations do is that they design the satellite, and then they use the launching through some companies. يعني. So here in Qatar University we have the CubeSat project. It's led by our colleagues in electrical engineering, and at some point they have to use a launching company to launch it. يعني. And this will طبعا of course will have very limited يعني services for projects and things like that. يعني. What is the name? Inmarsat ده. يعني what I'm trying to say is that it becomes very easy nowadays to launch these types of satellites. يعني. The geostationary satellites, but we need to talk about the characteristics. This is the specific distance of these types of geostationary satellites. They complete rotation exactly 1 day, similar to the rotation of the Earth. So it's synchronized, in which case they have the same footprint on Earth. They have fixed antenna positions and no adjusting necessary, because you have, of course, multiple antenna, by the way. You have multiple antenna and you have multiple beam spots and these types of geostationary satellites. But you don't have to do any kind of handover ولا حاجة. That's why you don't have to do مثلا beam forming. You don't have to do handover between one satellite and the other, because you only have 3. So basically, they are used as relay to relay the traffic back to the gateway. That's it. You don't even have satellite links. You don't have ISL links at all in geostationary. You don't have this. So satellites typically they have large footprint, usually around 34%. So you can have only 3 deployed in different parts around the equator, and that's all. Of course, as you can imagine, because you have to have inclination of 0, usually for geostationary satellites, the coverage in the North Pole and the South Pole is usually very tricky, right? So that's one of the issues. يعني. Bad elevations in areas with the latitude 60 degrees due to fixed position above the equator. So that's what we're talking about. Of course, because of the very large distance and very high altitude, you have to use transmit power in the range of sometimes close to 10 watts due to that distance. And not only that, this is only to have any type of communication. But regardless, you have the propagation delay is in the range around maybe 1 second. So that's why in these types of orbits, you can have data rates in the range of 10 bits per second, not kilobits, bits per second, 10 bits per second. So usually which was, it uses only data bits like 10 bits per second, something like that. Okay. And high latency usually in the length in the range of 250-75, which is almost like half a second. Yeah. So this is not, of course, useful for global coverage for small mobile stations and data transmission. Of course, data transmission and data services becomes very, very cumbersome in these types of satellites. And that's why it's usually used for TV broadcast, because as we said, TV is like one way. You don't have to have bidirectional communication. So for broadcast, you don't have to worry so much about the latency. صح? Because it's one way, right? يعني if you broadcast a signal, you can wait 1 second, but once the signal comes, everything else comes, right? It's not like we're talking conversation and everything is sequential. So in that case, the bidirectional latency becomes a big issue. So we have to have like a very fast response, right? In TV, we don't need that. So that's why it's commonly used for TV broadcast, not more than that. And that's how the mobile devices, they used to look like back in the 90s. So LEO, as we said, LEO is the most common. In that case, the radius, the small r, is between 500 kilometers to 1,500 kilometers above Earth. It's still circular. The visibility of the satellite is usually around 10 to 40 minutes. And what that means is that if there is a specific mobile user on ground on Earth, it can associate itself to the same satellite for 10 to 14 minutes, not more than that. And then it has to hand over to another satellite. And that's why for LEO systems, usually you have high constellation, because as you can imagine, the footprint on Earth is smaller, much smaller, right? So you need to have high constellation of satellites in the LEO orbits. واضحة دي؟ So the satellite itself has to move, has to rotate, right? So a specific point on Earth will have access to that satellite for 10 to 40 minutes, not more than that. And then it has to move to another satellite. In that case, latency is in the range of 5 to 10 milliseconds, and that's when we start to have any possibility of data services. We can have voice calls in that case. It becomes possible. Geo is impossible to have any kind of voice conversation or data services. ماشي كده؟ Of course, smaller footprints and better frequency use. Why? Because for geostationary, as you can imagine, we have only 3 satellites, and the footprint is very large. So usually we use 3 different frequencies for the 3 satellites, and that's it. ماشي? But here, because smaller cells, similar to the small cell structure that we talked about, because we have smaller cells, the coverage becomes smaller, so that allows you to have the same frequency in other footprints, which are far from this one. So there's no big overlap between the... So frequency reuse becomes better in the case of smaller footprint. But now handover is necessary. You have to facilitate handover between the different satellites. So a mobile user has to be able to hand over between the satellite more frequently. And of course, in that case, many satellites are needed, not just 1 or 2 or 3, similar to GEO. Here, we have to have in the order of at least مثلا 20, 30, and so on and so forth. And of course, it's more a complex system, because if we're talking about tens of these satellites which are moving, ماشي, the control and the management of, for example, the user to satellite association becomes more complex, of course. ماشي? So examples of these are commercial. Of course, you don't have to memorize these names. Erdium has been deployed in 1998, and it contains 66 satellites in a LEO orbit in this range. Global Star, these were competing, two competing organizations that they have deployed, but both of them are obsolete now. Of course, the data rates here is in the range of tens of kilobits per second, not more than that. We're talking about 10, 20 kilobits per second, something like this. So we start to have some possibility for voice conversation. Voice conversation becomes possible, but data service is still limited, still very limited. In a later stage, other satellites, they started to actually have even internet service provisioning. And users, they subscribe to satellite communication through certain organizations. And these organizations, they provide data services to users, and the users, at any point of time, they can communicate to the satellites or to the ground-based stations at any point of time. تفضل.
Here in the LEO systems, we always have to push them. Gravity will pull them to the air. Depending on the circulation period, you can still have balance. Well, that depends بقى the circulation اللي هو ال F circulation frequency, it controls the centrifugal force, صح؟ ماشي؟ So depending, if you control the speed in such a way that you circulate around Earth with a specific frequency, you can still maintain the forces. واضح ولا مش واضح؟ So we push them to speed them up.
هو depending على centrifugal force. You need to control the centrifugal force to be equal to the gravitational force. ماشي? That's possible through controlling the speed. If you want to move it faster, then you have to faster معناها it gets pulled out in outer range. So you need to use fuel to bring it back to the same orbit. Okay? If you use slower speed, then it gets attracted more to Earth. So you also need fuel to push it back to the orbit. Okay? But if you control the rotational speed in a specific way that balances the two forces, then you use the minimum amount of fuel. You don't have to do any control to the location of the satellite. ماشي؟ MEO or medium Earth orbits, they work in this range 5,000 to 12,000 kilometers above Earth, and usually they are slower moving satellites. Usually they are the LEO, they move faster, and less satellites are needed, of course, because as you go outer, the footprint becomes larger, so you need less number. And simpler system design, because if the footprint is large, then the frequency, the number of these satellites becomes less, and the control or the management of this satellite becomes also less in terms of overhead. طبعا, of course, you can facilitate the handover. If you don't want to support handover, it may be possible for MEO, but in that case, you have to have communication between the satellite and the ground-based station or the gateway more often. It has higher latency, so instead of talking about the fact 5 to 10 milliseconds, here we're talking about 70 to 80 milliseconds. It's still possible to do any kind of data services here, but the latency is significantly high. This is the only example, and again, nowadays it's much less to have satellites in that MEO orbit. Type in terms of routing. As we said, the mobile user can communicate with the satellite, but then there is like some routing decision that has to happen. Of course, you can route the traffic to the gateway, but then you have the high latency through the fact that you have to route the traffic back and forth from Earth, and in that case, the latency or the total delay becomes more. Or you can use the inter-satellite links, but the problem is that not all satellites they have the inter-satellite link capability. Not all of them. Even حتى LEO satellites sometimes they don't have this capability. So it depends, because these usually they use special type of microwave links or laser links, as we said, and that's not supported in all types of satellite deployments. So depending on whether you have ISL or not, you have to have like some routing decision in that case. So typically for routing, we need to have reduced number of gateways possible, in which case we have only one uplink and one downlink. That's it. In between, you can use ISL to route the traffic through the different satellites, especially if these satellites in the LEO orbit or they are close to each other. Usually the communication here becomes very, very fast. But if you send it to Earth and then you send it back up again, the latency becomes really, really high. ماشي? So we need to forward connections or data packets within the satellites through the ISL as much as we can. But not in all cases it's possible. ماشي? Only one uplink and one downlink. Usually that's our goal. We try to achieve that, but not in all cases it's achievable. In all cases, there are more complex focusing of antenna between satellites, because now these satellites, they have to have antennas for communicating to the mobile users, and they have to have special antennas to communicate with the other satellites through ISL link, as we said. So this requires different focusing of these antennas to facilitate the inter-satellite links. So that complicates the antenna architecture on the satellites usually, and that's why, as we said, not all the satellite deployments they use ISL links. The other problem as well is that these satellites they move. As they move, and the users on Earth they move as well. Of course, not in the same speed, but of course, the users also, they move. So that actually creates a complex situation that you need to deal with the multipath fading as well as routing, and you need to work on these two issues concurrently. Of course, if they move, and as we said, you need higher fuel consumption, especially if you need to do correction to the position of these satellites. And correction is not only needed, by the way, to balance the forces. Sometimes it's needed to facilitate this ISL links. Because if these satellites, they move with different speeds, this distance becomes larger or smaller. And especially if you have different constellations of these satellites in different in the orbit, these distances, because they move, these distances they vary. Okay, so I can have this the decision to send to this satellite or to another satellite on this side, okay, or I can use fuel consumption to try to correct my position in a specific position, and then I start the communication. So routing sometimes requires fuel consumption to correct the position of the satellite to facilitate the efficient communication. That makes usually the lifetime of the LEO orbits in particular. It makes the lifetime slightly shorter, يعني significantly shorter compared to GEO مثلا. ماشي. So Iridium, as we said, and Teledesic planned, they have the ISL link capability. So this ISL link capability, it's good in terms of
efficient communication, but as we said, it creates this complexity of routing, as well as we have to control the position of the satellite to have efficient communication, and that usually requires some fuel consumption. So having this ISL is really is tricky. It's not easy, and that's why in some satellite deployments like GlobalSat, GlobalSat is another example that we talked about in LEO. They don't support the ISL, and but that causes the fact that you have to use different gateways in different areas on Earth to facilitate the communication, and even then you have very high latency due to propagation. Okay. تفضل.
You mean by fuel consumption, you mean fuel ولا solar power?
That's a good point. طبعا typically they use fuel consumption. You can use the solar power as a renewable energy source. ماشي? To also generate some energy for control. But in all cases, you need some kind of energy which controls the mechanical system to correct the position of the satellite. ماشي؟ طبعا most of the energy usually comes from fuel اللي هو الفول consumption. ماشي؟ Similar to cars. But solar cells they are typically used, but usually as a complementary source of energy, not as a main source of energy. طيب, localization of mobile stations is actually a very important thing, because in satellite, especially if we use satellite for telecommunication and voice calls and things like that, localization becomes very important, صح? Because we need, if you want to dial مثلا and have voice conversation to another remote mobile device, then you need to localize where that device is. So the mechanism for localization is similar to GSM with some differences. In GSM, if you remember, we first, when we dial a number, we have to go to the home location register to get the geographical location of that particular device, and then we connect to the MSC that covers this geographical location, and the MSC will then broadcast signals to all the mobile, the base stations in this geographical area until we reach to the mobile user. So that's the way we locate where the user is. Here, طبعا, it's very much similar to gateways, because gateways they actually facilitate the interfacing between satellite network and GSM network. They also use HLR and VLR, similar to what we have discussed. In addition to this, we have another factor or another register for satellite communication, which is what we call satellite user mapping register. So this is part of the gateway, and the gateway maintains this SUMR, which is like, you can think of it as a database that maintains the association between the mobile user and which satellite it's connected to. So this gateway connects with multiple satellites, and it maintains in this SUMR the association between the mobile user and the satellite. So if I need to reach to a specific mobile user for voice calls مثلا ولا حاجة, I have to consult this register to know which satellite that this user is connected to, and then I have to send to this satellite the signal to send it to the mobile user in order to establish the end-to-end call. طبعا this whole signaling and stuff only exists in telecommunication satellites. طبعا in TV broadcast satellites and all of this, we don't need to do this because it's one way. تمام? So this is only needed in telecommunication satellites. ماشي? So localization of mobile station via the satellite's position, requesting user data from HLR, and then updating the VLR and the SUMR. So when we do the handover, between the different satellites, we'll talk about the different types of handover in that case. We have to update VLR as well as the SUMR with the new association of the user to the satellite. ماشي? So when we call a mobile station, we do by localization using HLR and VLRs and similar to GSM, and then we do the connection setup اللي هو ال end-to-end link setup, similar to what we have discussed before. But this will include by the connection, the extra connection between the gateway to the satellite and satellite to the mobile user. And that requires the consultation of the SUMR, or getting the association of the user from the SUMR. So in addition to HLR or VLR, we have the SUMR now for satellite. So this is what we need to talk about for localization. And hereby we have other types of handover. So similar to GSM, in GSM we have intra-BTS handover, inter-BTS handover, inter-BSC handover, and inter-MSC handover, remember? Yeah, and inter-system handover. We'll talk about all these types. And here we have similar things. So we have intra-satellite handover. Hereby we have to hand over between the spot beams اللي احنا قلنا عليهم. Spot beams معناها is like you are handing over between different antennas on the satellite, but within the same satellite. يعني. So you're moving from one spot beam to another. By spot beam we mean a small part of the footprint that is covered by a specific مثلا antenna of the satellite. And you have the inter-satellite handover, so handover from one satellite to another. In that case, the mobile station leaves the footprint of one satellite completely. ماشي? And that's due to sometimes the movement of the mobile user or the movement of the satellite itself. Like I could be مثلا moving in this direction, and the satellite is moving in that direction. Okay, so in that case, you have to do handover to another satellite. Not only because you're moving, but because the satellite itself is moving. So even if the mobile user is stationary on Earth, it may have to perform also a handover to different satellites. And there is a gateway handover, which means that now the satellite, because it moves, okay. So because it moves, it needs to hand over from one gateway on Earth to another. واضح كده? So you may have actually multiple gateways on Earth that communicates, each one communicates to multiple satellites, right? So when the satellite circulates, it may move away from a specific gateway, so it needs to hand over to another gateway. Or inter-system handover. Inter-system handover here means that the user is moving, and now it's getting into the range of a base station, a ground base station as part of GSM. So we are doing handover from satellite to GSM, or from satellite to 3G, or from satellite to 5G, right? So that's inter-system handover. So in that case, we have to move the technology altogether. I have to also mention here that some of these handover may be done in as soft handover or hard handover. Remember, by hard handover here, we mean that the mobile user, it allocates the resources, but at any point of time, it communicates to only one base station or one entity at a time. Okay. So even if you allocate the resources on both sides, but you have to do the switch and you communicate only with one entity at a time. So you have to communicate with one base station and then you move to another base station, one at a time. That's it. By soft handover, we mean that in a specific point, you may actually communicate using multicast to both base stations. We talked about this in 3G, if you remember. This is a soft handover. And we use multicast sometimes for diversity, to maintain the SNR for the specific user, whether in the uplink or downlink. So we use that for diversity, okay? So any of these handover types, again, can be soft or hard. Of course, if we're talking about old satellites, they usually use hard handover. ماشي? Nowadays, of course, as you can imagine, Starlink and the recent deployment of satellites, they use بقى soft handover. They use very sophisticated techniques, which we will talk about. So these are examples. Of course, as we said, Iridium here is Iridium and Global Star and Teledesic. All of them are LEO. Okay, and ICO is MEO. So as you can imagine, the numbers here are relatively higher, and here is low because the footprint is larger. So here you can cover the whole Earth with a low number of satellites. This is the altitude. This is in terms of kilometers, of course. So as we said, this is from 500 kilometers to 10,000 kilometers or something like this. So this is also LEO, and this is LEO. This one is relatively high, above 10,000 kilometers, which is MEO. So the coverage here depends طبعا على ال footprint. It may cover the whole Earth, or it may have some blind spots in certain area. So Iridium here provides, with this number of satellites, it covers all parts of Earth, which means global coverage. Here, that limits the coverage of this types of satellites. So it does not cover 100% of Earth. Elevation here is this is the minimum elevation through which you can have any type of communication. So here 8% means that less than 8% you don't have communication. Here less than 20, so not percent, sorry, 8 degrees. Less than 20 degrees you don't have communication.
It is 8 degrees from 90 ولا 8 degree?
لا 8 degrees. 8 degrees معناها يعني this is the angle between the beam from the satellite to Earth and the horizon. Okay?
Not from the 90.
لا not from the 90, no. So this is the frequency, this is the carrier frequency. ماشي? So طبعا here for Iridium we have ISL. As we said, for Global Star we don't have ISL. ماشي? Which is interesting because in LEO and with this number of satellites and you don't have ISL, this means that you have higher possibility of communicating to the gateway. And as we said, this actually reduces the efficiency drastically because you have to communicate and go back up. And so here in terms of latency, it becomes really high. ماشي? So in terms of bit rate, that's why here bit rates, of course, here we're talking about يعني one communication. So that does not take into consideration the fact that you have to go up and down, because that if you increase the latency, that of course affects the throughput as well. But this is the data rates. ماشي? So here 2.4 kilobits per second, here 99.6. If you remember, the lowest data rate that we talked about in GSM was 9.6, the lowest, even without using 2.5G ولا GPRS ولا حاجة زي كده. Here طبعا it's less. Here for the Teledesic is a little bit recent deployment, and they maintain high data rates. And of course Starlink, which what we have nowadays, they support much higher data rates, as we will see. The lifetime, this is 5 to 8 years, which means that these satellites, they need to be renewed. They need to travel down to Earth, and you have other, replacement of these satellites every 5 to 8 years. For MEO, it's usually a little bit higher, and for GEO, it's even higher, because again, the attractive forces becomes smaller as you go further, and that allows you to simply have this balance easily, and the footprint is larger, and that allows you to have less amount of fuel consumption to keep correcting the position. ماشي? So this is the cost, of course. يعني we don't have to be concerned so much about the cost. يعني. So this is the last slide, I guess. So for Starlink system, Of course, this is deployed by SpaceX. So that's an imaginary picture of how you have the constellation of all these satellites. You have, as we said, around 6,000 satellites. Of course, they are in one orbit, but definitely in different LEO orbits that covers different parts of Earth, right? The initial deployment was 2019, and the purpose was by a global high-speed internet service. And that's a very challenging objective, to have high-speed internet service. Which is comparable بقى to تخيل انت 4G و 5G with satellites and with all what we have studied so far. It's really challenging. It's a very far-reached objective. So you have to use so many sophisticated techniques and very high technology to maintain really data rates in the range of close to 300 or 500 megabits per second, which is close to what you can get in 4G and 5G. And of course, the biggest advantage here is that you have coverage for every point on Earth. There is no remote areas anymore. Here you can cover everything. You can use it بقى for applications here are huge So the types of orbits that we're talking about here is LEO, as we said, and we have around 6,000 active satellites, which means that technically you may have more than 6,000, but only 6,000 active at any point of time. The speeds typically in the range of 220 megabits per second, which can be actually they are trying to increase this.
Actually, it is really there, exactly 220 megabits.
Yes. So the key features هنا بقى, in order to maintain this high data rates with the low latency that we're talking about, with the high latency that we're talking about, of course here there's no question, you have ISL. You have ISL. You have only one uplink and one downlink. You cannot afford having multiple downlink communication in that case. You have only one high link, and of course between the satellites you use very high laser, very high speed communication through laser communication using a line of sight. Of course, they use MIMO beamforming to direct the beam towards the user, so even the satellite can control the beam to a specific user to have this high-speed data rates. You have adaptive modulation, of course. They use high QAM بقى. Here they use بقى QAM in the range of 128 or something like this. And of course, adaptive here means that depending on the signal strength and the signal-to-noise ratio, you may actually increase the QAM level or the constellation level or reduce it based on the SNR. We talked about this, right? So adaptive modulation encoding and very large bandwidths, because here we're talking about carrier frequency of 4 gigahertz. In that range, you can have fairly large bandwidths, because this range of spectrum is fairly wide, and you can have large bandwidths, in which case اللي هو في الMM wave range. In that case, you can have very large bandwidths, and using large bandwidths, طبعا if you the channel equation it's proportional directly to the bandwidth. So if you have large bandwidth, you have high throughput. So that's how you can really maintain very high data rates. طبعا here the correction and the estimation of the location of these satellite has to be extremely accurate in order to control بقى ISL والcorrection of location of these satellites, to have طبعا هنا طبعا في mesh connection between all these satellites. ماشي. So you have very complicated mesh communication. Routing here is extremely complex. With this number of satellites, مثلا 6,000, you can imagine the amount of routing decisions or routing combinations that you have. You have mesh routing, very sophisticated mesh routing here. And all these links, they have laser communication, as we said, so you have line of sight. It's really complex يعني. So to be honest, it's really impressive to have يعني internet service provisioning using satellite communication with this high data rates is very, very impressive يعني. It's very impressive.
Doctor, but we need the special receivers on the earth, like a dish or something like that, or we can use our phone.
لا phones. Of course يعني they may actually require special modems in home مثلا for home internet service provisioning. They need to have special base stations.
Now, Doctor, they started with special dishes just for the
Yes.
And special router.
Yes. They started with special devices. Yes, special devices. But يعني using يعني this range and these techniques and stuff, you can integrate the transceiver for Starlink easily with mobile. Currently, it's not done.
Currently, the latest iPhone, I think there is emergency satellite code.
Yes.
But I don't know if
لا emergency لا not necessarily using Starlink. But you can have satellite communication using the mobile phones. It's possible, but usually you have to spend high transmission power. The transceiver is possible to build it within the mobile phones that we have nowadays, although in many cases it's not done. So you have to have special transceiver to do this. So until today, I guess you have to have special mobile devices until today. But I think if it continues like this, definitely you will have iPhone and all these mobile phones. They will integrate this network and this technology in the phones in the upcoming versions. Definitely. And
so base stations will be at the risk.
ليه؟
You mainly like you want to use the satellite directly without.
ليه at risk? You mean from a security perspective? يعني?
No, like they get rid of it.
You mean لا يعني احنا يعني احنا we have hotspots and we have base stations صح nowadays. Can you مثلا imagine that you don't have hotspots, Wi-Fi hotspots? No. وعلى فكرة احنا we have the concept of femtocells and microcells in 5G for the last 20 years, and until today nobody has replaced the Wi-Fi at home. Even we talked about the possibility of having femtocells at home to replace the Wi-Fi خالص, but it never happened. Okay, so we'll see. يعني احنا بالنسبة لنا احنا we watch and we so there are multiple technologies and there is race and we'll see. يعني in some cases as users احنا we are opportunistic. Whoever will give us the best service will try it. And you may have multiple options of services. This will have definitely its own advantages, especially with coverage everywhere. فطبعا يعني it's very attractive, but it has a cost, of course. So we'll see how it goes يعني.